Hello again, everyone. This is chapter 6.3, which is called the dual problem. Here we'll be seeing minimization with problem constraints of the form greater than or equal to. And first off, I want to get out of the way what exactly a dual problem is. And here I say a minimization problem with greater than or equal to constraints can be associated with a maximization problem. So this coordination or association between these two max and min problems is known as a dual problem. So here's an example. I give this minimization problem. We're asked to minimize this objective function with these constraints, and this actually corresponds one-to-one with this maximization problem. The whole purpose of this is we want to use what we learned in 6.2, the Simplex tableau method. But in order to create a Simplex tableau, we need slack variables, and slack variables aren't really a thing when you're greater than or equal to, because you'd have to subtract to get to that point, not add, and it kind of defeats the purpose. So what we're going to do instead is we're going to transform somehow our minimization problem we're trying to solve in this section into a maximization problem with less than or equal to constraints that we can actually associate with and then finally use our Simplex tableau methods. But the question is how? First off, before we see how, let me say that we'll always minimize our objective function we'll always call C. Our maximization objective function we always call P. Normally the reason why is because the direct application problems that we use this technique for are for minimizing profit and maximizing profit and minimizing cost. So P for profit, C for cost. Notice also here there are X variables, here there are Y variables. So this is one of the reasons why we kind of went away from the previous problems we saw where we use X and Y. Instead we just use X sub 1, X sub 2, and X sub however many variables we have, because we can associate it with 1 and Y. Now, the solution we get for the maximization problem won't exactly be that solution for this one, so it's not like X's are equal to Y's, but there's an association we'll see. So we'll see that right now. If you look back at the previous example and try to find some pattern and connection between the two problems, there actually is a pretty simple pattern, and it has to do with what is called the transpose of a matrix. Basically, we're just kind of shifting things. So here I say the transpose of a matrix A is denoted A to the T. So A to the T is read A transpose. And this is the matrix whose rows are the columns of A. In other words, the rows and columns are swapped. So here, if A is this matrix and B is this matrix, we're going to find the transpose. So the transpose of A will have, well, let's see. So the first row will be the first column. That's how we do that. So the first row here, 3, 2, negative 1, is now the first column of A transpose, 3, 2, negative 1, just like this. And the second row is now the second column. So that's 0, 2, 3, just like this. So basically we just do this kind of reflection. The first row becomes the first column and vice versa. So same thing, if you look at the first column here, 3, 0, that's the same as this first row, 3, 0. And now what about this 3 by 1 matrix? For this 3 by 1 matrix, well, it's only one column, so now it's going to be only one row, 3, negative 5, 0 for its transpose. Okay, and now we're going to actually do the problem we just did and try to see how we can, that we just saw anyways. Now we're going to redo the problem that we saw previously and actually come up with that that maximization problem that corresponds to using this idea. So let's see if that works. Okay, so let's recall the first example we looked at. We have this minimization problem, and we're going to first write a matrix. Now the matrix we're going to write, we're going to call A, and just to give you an idea of what A is going to be, think back to the Simplex tableau that we saw. Remember we had these lines, and what did we always write on the bottom? So below this line, we always wrote the objective function. So that's actually what we're going to do here. We're going to actually write the objective function down below. So the objective function is going to be, well, it's going to be 16, 45, and then 1. In other words, this will be the x1 column, the x2 column, and this will be the equal to column. And in this case, it's equal to C, but it's 1C, basically. Okay, so now what about the other ones? So the other ones will just be as is. So that's going to be 2, 5, 50, 1, 3, 27. Okay, now this is matrix A. This is not the same as Simplex tableau but it's a similar construction. So we're not actually using this to solve the minimization problem like Simplex Tableau we use to solve. Here we're just using this to translate this into a maximization problem, which we can then use the Simplex Tableau method on. So now, if that's A, well, what is the transpose of A? What is A transpose? Well, ignoring all the lines, let's see. The first row is 2, 5, 50, so the first column will be 2, 5, 50. Okay, the second row is 1, 3, 27, so our second column will be 1, 3, 27. And now finally our third row, 16, 45, 1, becomes our third column, 16, 45, 1. Now we can write our lines. Okay, the only thing now is that, well, now we don't have x1 and x2 anymore. Now we have new variables that we've kind of introduced here, and these will be y1 and y2. Similarly, this was the, well, it was the coefficient of C, now it'll be the coefficient of P. So what this will correspond to actually, so just to like write it above, we're going to have P is equal to 50 y1 plus 27 y2. Okay, our constraints will be 2y1 plus y2 less than or equal to 16, 5y1 plus 3y2 less than or equal to 45. And of course we also have those non-negative constraints, y1 and y2, the only variables we have here, are greater than or equal to 0. So notice when I converted this back into a problem, now it's a maximization problem actually. So now we'll say maximize instead of minimize this P function subject to these constraints with y1 and y2. So this is exactly how we're going to convert a minimization problem into a maximization problem. Now we can apply our Simplex Tableau method. There is a little bit more of a catch though. So there's some small detail that I'm leaving out, but we'll actually continue this problem in the next screen. So I'm gonna move this here. It's spelled maximize wrong. I'm gonna move this over here, and then we're gonna actually continue with actually solving this, and then we'll see how it corresponds to a minimization solution. So we'll see that right now. All right, so now this is our maximization problem that we agreed on, that we transformed our minimization problem into. Now we're going to convert this into our Simplex Tableau. I need to explain a few things because, like I said, I'm leaving out a little bit of detail here. But first, let's just kind of create the structure of it, and I think that's okay. So we'll have a y1 column, a y2 column, because those are the variables. And we can just start filling things in. So for the first two equations, we're going to have 2 and 1 for these coefficients, and that's going to be equal to 16. Right? We'll also have a p column here, and we'll have our two slack variables. I'm going to hold off on those because I need to explain a few things. And now let me fill in the rest. So this is going to be, for the second equation, 5, 3, 45. And the last one here will be our p equation, which is just our objective function. But again, we have to subtract these to this side. So it's going to be negative 50 for y1, negative 27 when you move that over for y2, and that's going to be 0 of the slack variables. So 0, 0, and then for p it's going to be 1 because there's one p on that side once you move these to the left. And that's equal to 0. Okay, p is represented 0 times in these equations, these inequalities. And now finally for the part that is the killer detail I was leaving out. The slack variables, you were probably expecting me to write S1 and S2. It's a little weird, but we're actually going to use X1 and X2. Why we're using X1 and X2 is so we can get our solution right away and we don't have to translate back. And as it turns out, X1 and X2 are essentially the slack variables for this problem. So it's a little hard to explain the details of that, but for right now, I guess all we really need to know is that these are slack variables for minimization problems after you convert them into maximization problems. Okay, so we're going to add 1 of x1 to, let me do that in black, first inequality to make it equality, and then 0 of x1 but 1 of x2 to the second one, just like we normally do. And now we're going to apply our pivot method here to solve the problem. So let's see. So the first negative one, or the most negative one I should say, of our indicator variables is right here. So this is going to be our pivot column. And then we're going to divide these numbers by these. So notice 16 divided by 2 is 8. 45 divided by 5 is 9. 8 smaller, so I'm going to go with the first one. And that's going to be our pivot row. So now 2 is our pivot element. So I'm going to divide everything by 2. So let me just write our result here. So I'm going to try to continue in this fashion. So we're going to have 1/2. Well, actually we're dividing everything by 2. So the 2 divided by 2 is 1. There we go. Then 1/2, then another 1/2, then 0, 0, and then 16 divided by 2 is 8. Okay, and now what? Well, now we want to multiply this by negatives of these numbers so that when you add them together they cancel out, which is what we saw in 6.2. So multiplying this by -5 will leave us with -5, -5/2, -5/2, 0, 0, and -8 over 2 is -4. Okay, and I'm sorry, I'm multiplying this by -5, aren't I? My mistake. That's -40. Okay, so now that we have that, we're going to add it to the original of the second row. So it's 5, 3, 0, 1, 0, 45. When you add these together, you get 0. Let's see, 3 minus 2.5 is 1/2, so it's going to be 1/2. And that's going to be -5/2. That's going to be 1, 0, and 45 minus 40 is just 5. Perfect. Almost done, just one more. So now I'm going to multiply, well actually not one more, because then we have to maybe do it again, right? So I'm almost done with the first pivot, I should say. So now let's see. So I'm going to multiply the top row, or pivot row, by 50 to match this -50. So just to erase our work here, let's see if we can show that. So multiplying the top by 50, we get 50, 1/2 times 50 is 25, so there's 2 25s, then 2 zeros, and then 50 times 8 is 400. And we're going to add that to the original of the third. So -15, -27, 0, 0, 1, and 0. So we'll naturally get 0, -2, 25, 0, 1, and 400. Perfect. Whew, nice. So we finished our first pivot, and now we're going to do one more because we have a negative indicator still, right here, 2. -2. So this will be our next one. The detail I'm leaving out, of course, is that y1 entered here and exited here. So this is now our y1 row. This is still y1, this is still y2, this is still x1, x2, this is still p, and so on. But right now this is x2 still, y2 hasn't exited yet. And we're assuming it's going to exit here, but just to see, dividing each of these numbers by 1/2, remember when you divide by 1/2, you're multiplying by 2. So we get 16 and 10, 10 smaller. So we are indeed going to go with the second row here. So this will be our pivot element. So we need to multiply it by 2 to make it a 1. So let's see what we get here. Let me use the equivalent matrix symbol, which I think is suitable. All right, so let's see. So the second row will now become 0, 1, -5, 2, 0, and 10. Perfect. And now what are we going to do to this? Well, we're going to multiply by -1/2 and then add it to this one, to the top one. Now notice doing that, multiplying by -1/2 is just getting back to this with negatives, so changing their signs. So let me write the work here below. So for the second row, multiplying by -1/2 is just going to be 0, multiplying this by -1/2 is just going to be 0, -1/2, +5/2, -1, 0, and -5. Again, just because we're going to get back to this, but changing their signs. Adding it to the original top one, let me write it above. 1, 1/2, 1/2, 0, 0, and 8. Adding these, we get 1, 0. 1/2 plus 5/2 is 6/2, which is 3. -1, 0. and a minus 5 is 3. Okay, and y2 is already exited. This is the y1 column, y2 column, and these were the x's as our slack variables, and this was p. This is also p. Whew, nice, so let me erase the work here, and let's do the bottom row finally. So what do we multiply this pivoting row by to match this -2 by its opposite, so by 2? So multiplying every entry in this row by 2 will give us 0, 2, -10, 4, 0, 20. Adding it to the original row 3 is 0, -2, 25, 0, 1, 400. And we get 0, 0, 15, 4, 1, and 420. Perfect. And now here is the beautiful conclusion that we'll make. So first off, we want to say that our maximum is 420. So our max to our maximization problem is p is equal to 420, and it occurs at what point? It occurs at the point y1 equals 3 and y2 equals 10. So 3, 10, where the first entry is y1 and the second entry is y2. But what this corresponds to actually is that we have a minimum for our minimization problem. Not for this problem, for our minimization problem that we amounted to, or that we started with, I should say. Our minimum is, remember it was c, that was our objective function for the minimization problem, and it is also going to be 420. But it is not going to happen at this point. It's going to happen at our x1 and x2 values. That's why we had to use them as our slack variables. And our x1 and x2 values, in order that they appear, are 15 and 4. So it's going to be 15 for x1 and 4 for x2. So this really is our answer. So perfect. That's essentially what 6.3 is. We're going to see a little more of a complicated problem right now, but that's the main idea. We're given a minimization problem, we convert it to a maximization problem by doing transpose, then we can use Simplex tableau methods that we saw from 6.2, and we have to make sure that the only catch there, so we have to make sure our slack variables are the x's, not s's, because they correspond exactly to the solutions, or the point anyways, where a solution takes place for the minimization problem. The max and min will be the same actually though. Alright, so there's a lot going on in this problem, so let's read, shall we? Let's see. So a food processing company produces regular and deluxe ice cream and 3 plants. Per hour of operation, the Cedarburg plant produces 20 gallons of regular ice cream, 10 gallons of deluxe. The Grafton plant produces 10 gallons of regular, 20 of deluxe. And West Bend plant produces 20 gallons of regular and also 20 of deluxe. It costs $70 per hour to operate the Cedarburg, $75 per hour for Grafton, $90 per hour for West Bend plant. The company needs to produce at least 300 gallons of regular ice cream and 200 gallons of deluxe. How many hours per day should each plant operate in order to produce the required amount of ice cream and to minimize the cost of production? What is the minimum production cost? So I'm going to write this on the board and I'll try to explain my reasons for creating the model, and we'll see if we can do it. Alright, so this is what I got here for the labeling and for the corresponding problem model, really, from the problem we just read. And I want to talk real quickly about how I came up with this. So I label x1 and x2 and x3 as the rates for these locations, Cedarburg, Grafton, and West Bend. And how I was able to do that is really I just looked at the keyword in the question and said minimize cost of production. Okay, so I looked at cost of production. I'm going to call that C. So the variables are going to be your cost because you want to minimize that. So naturally, the keyword I'm looking for isn't gallons. The keyword I'm looking for is how much per hour, so money. So that's what I saw, that there were 3 of them, so I'm going to label them corresponding to their locations. Now, where the gallons get into the mix is there are 2 types of ice cream. Those correspond to our constraints. We have a constraint for regular and a constraint for deluxe. Also, the keyword at least means greater than or equal to, because that's the smallest it can be. It can be bigger than that. So at least 300 gallons and at least 200 gallons were keywords I was looking for. And then these are how many gallons of each one corresponding to those locations that they make. So for instance, Cedarburg made 20 regular, Grafton made 10 of the regular, and then West Bend made 20 regular. And you can read and go back and figure out that this model is indeed correct. So I hope we're okay there. So the first thing I want to do is I want to write our matrix A. So we'll do that right now. In fact, yeah, I guess we could just do it right here. So let's see. Remember that we want to do it like this, so that we have our cost on the bottom. So it's going to be 1 for cost, and then we're going to have x1, x2, and x3 columns for each of those variables. So for the cost objective function, it's going to be 70, 75, and 90 for these coefficients. And what about for the inequalities or actual constraints? Again, we're ignoring the non-negative ones, so just regular and deluxe, basically. So we have 20, 10, 20. On the other side, we have 300. And here we have 10, 20, 20. And on the other side, we have 200. So this is A. Now let's see if we can find A transpose. And I think we can. I think it's pretty simple to just do it. But notice, it's not a square matrix like the past one. So that's one reason why this is a little more of a complicated problem. Also, obviously, there are more variables here, but you'll kind of see that that doesn't really become too much of an issue. So let's take a look at the first row and make it the first column. So we get 20, 10, 20, 300 like this now. And similarly for our second row is now our second column. So that's 10, 20, 20. And 200. So this should have been a 200. My mistake on that. And then finally, our third row is now the third column, 70, 75, 91. And we, of course, have those lines like this. And now the x's are gone. Now we have y's, our new variable. So I'm going to erase all this, move this over here, and then translate it into our maximization problem now. Good, so this was the transpose we just left off on, but now shifted over here, of course. And we're going to convert this now into a maximization problem. So the first thing is, what is our objective function? What are we trying to maximize? Instead of C for cost, it's now P, basically for profit now. And it's going to be this times Y1, that times Y2 is equal to 1 times P. So P is equal to 300 Y1 plus 200 Y2. Perfect. And we're maximizing this subject to what constraints? So subject to the constraints, let me make a little bit of space here. So the first one is going to be 20, 10, 70. 20, 10, 70. And then it's less than now instead of greater than. Remember, the inequality symbol flips when we do this transpose. Now 10, 20, 75. Good. And finally, 20, 20, 90. And of course, we also have our non-negative constraints. And the first thing you'll think is that this is quite funny, because if you haven't realized already, we lost a variable. The problem was 3 variables with the minimization, but now with maximization, all of a sudden it's not 3 variables anymore, now it's 2 variables. But we also have 3 constraints instead of 2, or yeah. So how do we continue from here? Well, let's try to set up a Simplex tableau. Let's see if we can figure this out. So to set up a Simplex tableau, we're just going to kind of follow the same procedure we've been following. Let's see how far we get. So I'm going to start with creating the entries. So remember, our variables are y1, y2. We're going to have some slack variables, 1 for each equation. There are 3 equations, and we're not going to use s, we're going to use x. So it's x1, x2, and x3. Very fitting, because those were the variables we had that we wanted to find, basically. We'll have a P column and then our other column. So hopefully we have enough space here. We need 3 and then 1, so I think we'll be okay. So this is going to be 20, 10, 10, 20, 20, 20. These numbers will be 70, 75, 90. Perfect. There's no p in these inequalities, so these are 0. We're adding x1 to the first one, x2 to the second, and only x3 to the third. So it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. Perfect. And now what about our objective function? Well, remember, we subtract these to the left so that we have 0 on that side for the p row. Good. And now we're going to have negative 300 y1, negative 200 y2, and 1p is 0 of the slacks. And our slacks go here, x1, x2, x3. I'm way out of space. I wrote this kind of too big. But I'm going to try to write a little smaller over here, and we're going to continue with our pivots. All right, so here it is. The only one thing I want to say, though, is that even though this may look overwhelming because it's a lot to look at, obviously, notice since we only have 2 variables, though, we only really need to perform, at most, 2 pivots. So we'll have to just see how it goes. So just to get started here, what is our pivot column going to be? It's going to be our most negative indicator, which is negative 300. So it's this column. And how do we find the rows? We divide these numbers by these entries. So we get 70 over 20 is 7 over 2. 75 over 10 reduces to, well, I guess we can write it as 7.5. 7 over 2, by the way, is 3.5. If you like decimals, you can write everything in decimal. But I just like fractions, so it's just me. But to compare, I agree, decimals are kind of where it's at. And then finally, 90 over 20 reduced to 9 over 2, which is 4.5. So clearly the smaller one is 3.5. So we're going to go with the first row as our pivot row. So this right here will be our pivot element. So now we're going to divide everything here by 20. So let's see what we get now. So we're going to get 1. That divided by 20 is 1 over 2. Then 1 over 20. Then we have our 3 zeros. And then 70 over 20, of course, is 7 over 2, or 3.5, but I'll write 7 over 2, just because I'm a fan of fractions. It's not a bad idea to like fractions, I guess. And now we're going to, let's see, I need to write some work over here. Hopefully we have enough space for it. Well, let's see. So this is, y1 is going to be exiting here, so might as well just write that. Let me label the other things here, just to get everything started. Perfect. This is x2, x3. Great. And that was p. Okay, good. So let's see. To get things started for eliminating this 10 to make it 0, we need to multiply this by negative 10. So multiply this row by negative 10, we get negative 10, negative 5. Negative 10 over 20 is going to be negative 1/2. 0, 0, 0, so 3 zeros. And let's see, we're multiplying this by negative 10, so what do we get here? Remember, this is 3.5 times 10 is 35, so it's negative 35. And then adding it to the original row 2, that's 10, 20, 0, 1, 0, 0, 75. Adding these, we get 0, 15, negative 1/2, 1, 0, 0, and then that's going to be 40. Perfect. Now for the next one, for the third row, we need to multiply the first row, or pivot row, by negative 20. And notice what will happen when we multiply this by negative 20 is we'll get back the same original first row, but all negated. So let's write that. It's going to be negative 20, negative 10, negative 1, our 3 zeros, of course, and then negative 70. Now the original row 3 was 20, 20, 0, 0, 1, 0, and then 90. Adding these now will give us 0, 10, negative 1, 0, 1, 0, and 20. Perfect. Now finally, for our last row, let's see. So I need to multiply this one by 300 to match this negative 300. So multiplying all of these by 300, let's see what we get here. I may have run out of space because it's too... I'm going to write the work here below. It's fine. So multiplying these by 300 will leave us with 300. Half of 300 is 150. 1 over 20 is half and then a tenth of that. Half of that was 150 and then a tenth of that would be just 15. Our 3 zeros. 7 halves times 3. Let me see. So that's going to be, I guess that'll just be 1050. You could do the math on that, but yeah, I'm getting 7 times 300 is 2100 divided by 2 is 1050. And then the original last row is negative 300, negative 200, 0, 0, 0, 1, 0. Adding these will leave us with 0, negative 50. Oh, the negative hurts because that means we got to do a pivot once more. 15, 0, 0, 1, and then those add to 1050, of course. Perfect. I ran out of space though, so I'm going to have to erase this, shift this up, and one more pivot to go. All right, great. So here it is, and now we're going to look for our new pivot column. Also, remember this was y1, that's where y1 exited. Good. So our pivot column now will be, this is our negative indicator, so that's our pivot column. Our pivot row, we need to divide these numbers by these. So 7 over 2 multiplied by the reciprocal of 1 over 2 is just 7. 40 over 15, if you divide that fraction by 5, you get 8 over 3, which is about 2.33. I think it's 2 1/3. It's actually 2 2/3, isn't it? It's 2 6. Well, okay. So 20 divided by 10 is now 2, and that's clearly the winner here. So we're going to go with the third row as being our pivot row. So this will now be our pivot element, so we're going to divide everything in this row by 10. So let's see if we can make things happen. So let's see, we've got y1, x2, this is now going to be y2 because y2 is going to exit here, so might as well write that. So p, good, we want to make sure I have enough space for our work. I'll do the work over here like last time. Right, so dividing every entry here by 10 will leave us with 0, 1, negative 1/10, 0, positive 1/10, 0, and 20 over 10 is 2. Great. Okay, yeah, so now let's see if we can apply the operations then. What do I multiply this by to get rid of the entry here in the first row? I need it to be negative 1/2, so I'm going to multiply everything by negative 1/2. Let's see what we get. So this times negative 1/2 is going to be, so I have space, so it's going to be 0, negative 1/2, positive 1 over 20, 0, negative 1 over 20, 0, and a negative 1. And now we're adding this to the original first row, so I'll write that on top. That's 1, 1/2, 1 over 20, 0, 0, 0, and 7 over 2. Adding these will leave us with our first row being 1, 0, 1 over 20 plus 1 over 20 is 2 over 20, which is 1 over 10, 0, negative 1 over 20, 0, and let's see, remember this is 7 over 2 is 3.5, minus 1 is 2.5, which as a fraction is 5 over 2. Okay, second row now, multiply this one by negative 15 to match that 15. So multiply these by negative 15, and we get 0, negative 15. 15 over 10 reduces to 3 over 2, so it's going to be positive 3 over 2 because of the double negative. 0, negative 3 over 2, 0, 2 times negative 15 will be negative 30. Good. Just making sure. Have things. Okay, looks good. The original second row will be 0, 15, negative 1/2, 1, 0, 0, and 40. Adding these will leave us with 0, 0. Negative 1/2 and 3 over 2 combine to 2 over 2, which is 1. All right? 1 plus 0 is 1. That's going to be negative 3/2, 0, and then finally 40 minus 30 is just 10. Great. Finally, the one we really care about, the bottom one. So let's see. I'm going to multiply this by 50 to match that negative 50 here for the bottom row. So multiplying every entry here by 50, we get 0, 50, 50 over 10 is 5, so that's negative 5, 0, 5, 0, and 50 times 2 is 100. Okay, the original bottom row here is negative 50, 0, negative 50, 15, 0, 0, 1, and 10, 50. Perfect. Hopefully you can see that. No, it's kind of squeezed there a little bit. Maybe it cuts off. But adding these, finally we get 0, 0, 10, 0, 5, 1, and 1150. Perfect. We're done. We're completely done. This tells us the following. this is our max and our min, depending which problem you're talking about, because after all, it is a dual problem. So let's talk about the max first. So our max is P is equal to 1150, and that occurs at what point? Well, this point is really a ordered triple, so there's three components to this point. There are y values, so it's y1, y2, and y3. y1 is 5/2. y2 is 2. And y3 is 0 because y3 never exited. In fact, there is no y3, is there? So, yeah, that's funny. So we don't even need a third entry because there is no y3. So it is indeed an ordered pair, not an ordered triple. So I misspoke there. But anyways, let me just write y1, y2. So we plug these into our original P objective function. You will get 1150 when you plug these y values in. Good. So now what does it say about, finally the one we care about, our minimum? Our minimum is C. Remember our objective function there was C. And it's also equal to 1150. And it occurs at what x values? Well, just to relabel things accordingly, this is y1, y2. These were our x's, and this was p. So the y's are these right here, 10, 0, 5, in that order. So it occurs at the point 10, 0, 5. This is an ordered triple. Perfect. So what this means, if you want to, I guess, write it in some conclusion, is that to minimize our cost per day, we would have to use a total of 10 hours for the first plant, 0 hours for the second, 5 hours for the third plant, and the cost per day would be this much, it'd be $1,150. But instead of writing that in words, just because I don't have space and I don't want to erase again, I'm just going to box this. But of course, the last thing we have to do really is interpret that. So I really should, but you can do that on your own, I guess. Awesome. So that was it for 6.3. That's actually it for chapter 6 in general. So I'll see you in the next videos for chapter 7. I really hope you enjoyed. We only really did 2 problems if you think about it, but they were good problems. We saw the process, and that's really what matters. It's a little more difficult, but again, it's just using the same thing, building on the same thing we saw from the previous chapter. So just keep on building this process and see how it works in different situations. And here we saw it for the minimization problems. So really hope you enjoyed. I'll see you in the next videos. Thanks for watching.